technical experiment number 8 deals with PV power panel alignment. So in this case we do have an artificial sun, which is a light, as you can see, and here we have 2 solar panels, and with this setup we can check, okay, what is the perfect angle for a PV panel to be aligned compared to the sun. We can check 2 angles, meaning this one and that one. So there are always 2 components to align your PV panel to the sun. Usually if you do it on a rooftop, sometimes you don't have the chance to choose this angle because you can't rotate your own domestic home, but sometimes you can choose this one. For example, if you've got a flat roof or you're building, so you're not done yet, or you're putting up the PV panels on a green field of grass, and there you want to put them up in the perfect angle so that you can get the most energy out of your panels and produce the most energy to gain the most money. That's usually the purpose for doing so. So this experiment involves a couple of different components. So we do have a ESP32 microcontroller again, where the program runs on the chip. Then we do have 2 sensors. On the one hand here we do have a sensor. It's called the ENA219. It's a sensor which can measure voltage and current. In this case we're measuring the voltage and current from the panel to check what is the power outcome. And then we do have another sensor here, which is the MPU. The number I can't read in the moment, it's on the other side, but we'll have that in the documents. So by the way, all the documents are uploaded on our website of the University of Stuttgart. Check out down below in the description box where to find the link and where to find all the materials, including the program code, as I said, which sensors are used, which components a material list, the STL files for all the 3D printed parts, and so on. So feel free to do so. Back to the components here in this experiment. We have this sensor which is measuring the angle. That's why it's sticked to the lid and not to the ground box of the experiment, so that it changes when we change the lid, and when we change the lid we also change the angle of the solar panel. Inside the experiment you see the so-called experiment description card. We always have different colors for different groups. For example, on this one you see there's a red card inside and it's called group red. So what we tried is always to provide multiple of these experiments in different colors. So if you have a class with maybe 30 learners of yours, you want every student to be able to touch for himself and not just watching others doing this cool stuff. So we provided 5 technical experiments which we are using in our training for lecturers, for TVET lecturers and vocational school teachers, where we train them. So we do groups of 3 each, meaning that everyone is able to touch for himself, trying out the experiment, gaining new knowledge, and not just me in the front while teaching others, presenting the experiment, and everyone needs to sit there in his row and just watch what I'm doing. Yes, so these are the different colored groups, and here we have some informations on there, an IP address and a password. We don't need the IP address for this current setup because we're doing it via the Phyphox app, and therefore we've got also a short introduction on our worksheet. This worksheet is used in our training for the TVET lectures, as I said before. So this is not meant for learners, for students. Learners usually need a more like step-by-step guide. They really need to know, okay, where do I need to focus on? What should be my outcome? What is the actual task? Here we just came up with the research question, which is what is the optimal angle of a PV panel to generate the most energy? Because we are training lecturers who are professionals in their field. So yeah, they can think for themselves. So today they can figure out for themselves what is the best, how do I want to approach this experiment, what is my controlled condition, for example, that what we're doing with the artificial sun, because if I would use daylight. If it's a clear sky, I can use the sun, which is shining on Earth. But if not, if some clouds appear and so on, the intensity of the sun varies very quickly. And to eliminate this, we're using this artificial sun to have this controlled condition. We also have dependent and independent variables. The independent variable is the angle, and the dependent variable is then the outcome of the solar panel, which we're gonna measure. So with this experiment, I'm currently going over to the learning objectives you can have. You can teach your learners how to conduct an experiment. So what do you need to plan? Which variables do you need to measure? And so on. Yes, but besides that, other learning objectives would be also how to construct again this 3D printed housing of the panel. What is actually a solar panel? How does it work? Why do we want to put it into a specific angle? You could dive into the physics. Why is it that the one angle is better than the other? The energy is higher coming from the sun in one angle than in the other. But you could also do like electronics, how to choose sensors, how to connect them to a microcontroller, programming part. So there are a couple of things you can cover with this experiment. So as I said, that was my last point. Here's a short technical instruction how to use this experiment, and we're gonna do that together. So it says download the Phyphox app from the Google Play Store or App Store. I have done that already. So on my iPad, which I'm opening now, here somewhere we do have the Phyphox app already. I can search it. Here's it, Phyphox app. Now we open the Phyphox app, and what we now want to do is activate Bluetooth on your smartphone or on your tablet, whatever you like to do, to use, and then open the Phyphox app. Okay, so we opened the Phyphox app. Our Bluetooth is already on, as we can see. So now we can add an experiment for Bluetooth device. So we need to press the plus button and say add experiment not from QR code. I was wrong. We want to add an experiment from Bluetooth device. And now we need to find the Bluetooth devices. So these experiments need to be switched on. Sometimes the power bank switches off if one doesn't use the experiments. Now, as you can see here with the appearing Bluetooth devices, you can find the PV power group yellow. If we press on that one, it's loading. So now it's connecting this Phyphox app, which is free of charge. It was developed by a German university. And what this app does, it takes all the sensors which are in either your tablet or in your smartphone, and you can get the data which these sensors are measuring, and you can use them for your own purpose. For example, the microphone, you could measure how loud is it in your classroom. Or you could take the acceleration sensor to see if you put it, like, for example, in a small scale remote car, what are the G-forces in that car, and so on. So you can use all the sensors inside your mobile device. But what we're now doing, we're not using the sensors of our mobile device, but we're connecting via the app, via Bluetooth, to our ESP32, and from here we will provide the data for the app, which it should show. So now we are in our experiment. We change to the PV angle. So for now the screen is empty, but we've got already the two axes, the angle and the output power. So now if we press the play button, it's recording the data, and now here we can change the angle of our experiment, and the data will be collected here on the app. So now I'm pressing the pause button that it doesn't carry on running. So now we have here the graph where we can see in the dependent variable is the output power, and the independent variable is the angle. So the angle is on the x-axis and the output power is on the y-axis. And here we see the maximum power point is somewhere here around 120 degrees. So with this setup, the sun shining like it does now, the 120 degrees would be the optimal angle to get the most energy out of the solar panel. And this is the whole experiment about. So the technology is doing a lot here for us already. We could do the setup in a simpler way where we only have a solar panel and then we have a multimeter and we're measuring the output and we're writing it down on a paper or we're putting it into an Excel sheet, and there we're calculating our own graph. But here the Phyphox app is doing it already for us. And what the Phyphox app should do, meaning what are the axes and how does it look like, that is programmed here on the little ESP32. So the university who programmed this Phyphox app, which you can install on any Android or iOS device, they provide a library, and with that library you can program this ESP32, and then you can send the data to the app on your device, on your mobile device, and you can decide when that is stored here on the ESP32 what should be shown there on the Phyphox app. So everyone in the world now logging into this one via Bluetooth will see the same picture because I defined it here on the small device what should be shown there. So now if I want to know what does it cost, I also want to have something like this. You can rebuild it yourself. As we said, we're providing all the data. There's no secret behind it, and we do have a material list. It's round about 70 euros, which makes in South African rand, for example, 1,400 rand. The most expensive part of this experiment is the friction hinge we're using here to hold the lid in place. So also there you could do a construction task to your students to find a different setup, which is maybe even 3D printable and not as expensive. Maybe one could print a friction hinge as well. We haven't tried. We haven't looked for a model if there is one already on the market. And the second expensive thing is the power bank. So you could use any power bank you already have, or you could plug in the USB directly into a plug. But we use this setup so we are mobile, we can distribute it to the learners and they can play around on their table with this device. So this is these two devices, as I said, the friction hinge and the power bank, they are around 30 euros already. So if you find a different solution for that one, your whole setup will get cheaper. And yeah, we have mainly, the mechanical parts are mainly 3D printed, some screws, the hinge, as I said, and from the electrical side, the ESP32, the solar panel, the two sensors, and then we still got a resistor and the ESP32 I mentioned already. Yeah, so that's it. It's a very simple setup, not a lot of components, and we haven't done a customized PCB yet. So we're using a universal PCB where we're soldering all the components on there. You could also use a breadboard to put all the components on. But if you want to carry this around a lot or transport it as we do from South Africa and to Germany back and forth, we need the components very good fixed onto the PCB that we don't reach our destination, want to do a training, and then we do troubleshooting because something is not right in the breadboard. So for us, it's a better solution to solder it onto a universal PCB. The whole housing of this experiment was also designed, again, using a CAD software. So this experiment is very nice to show the different relations between sun angle, PV panel angle, and you could also do like if a cloud comes in between, or if you have a diffuse day, sometimes you could shine the sun to the roof, which is not what the sun does usually, but you can simulate a clouded day, because on a clouded day the sun doesn't come from a specific point, but the light comes from everywhere. It's diffuse. So you can also simulate that with this experiment and play around a bit with sun and energy and try to figure out how renewable energies works.